Good morning. The first computer that I ever had was one of these. It was an Amstrad 6128 that my father brought home from work in about 1985 and put it in the corner of the spare room. And I got obsessed with this thing. Now, this was not a very good computer. It had some fairly primitive and rudimentary games. It had games that were so bad that as a 7-year-old kid, I believed that I could make better games. And so I thought, all right, well, if I want to make games, I need to figure out how to do graphics. And does anybody recognize the language that my slides are loading in here? This is Amstrad Logo. And that was my first programming language. I started out on Amstrad Logo, and getting the computer to draw pictures, I never went back to games after that, because there was this rush, there was this thrill when I typed in the lines of code and something appeared on the screen of the computer there that maybe nobody had ever seen before. Maybe this was completely unique and original, but I made it. I made the computer draw the thing that I wanted to see on it. And, you know, for me, that rush, that thrill of getting the machine to do something interesting, that has never gone away. Throughout my entire career, as a developer, as a architect, as a manager, building all kinds of different systems, I still get that little rush out of, hey, look what I made the computer do. Now, the world has moved on a lot since the days of my little Amstrad 128 there. And over the course of the next few days, you are going to hear from some of the best speakers in this industry about some fantastic, wonderful technology, incredible improvements in threading and performance optimizations, data structures, DevOps, all these kinds of things. And that stuff is useful. We can take that information and those techniques and we can go and apply them in our jobs to real-world problems. They have applications. But for the next hour or so, indulge me, because you are not going to learn anything useful, because we are going to talk about art. And there's this famous quote from Oscar Wilde that all art is quite useless, because that's why it's art. Like, if it was good at something, it wouldn't be art, it would be something else. But there is another quote about art from another great Oscar Wilde was Irish, sorry, Irish people, from another writer who hails from near the British Isles, Douglas Adams, who created The Hitchhiker's Guide to the Galaxy. And in the restaurant at the end of the universe, he has this quote, which is him paraphrasing Shakespeare: "The function of art is to hold a mirror up to nature, to help us better perceive and understand our world and our reality. And if we want to hold a mirror up to nature, first we have to invent the mirror. And that is where science and technology come in." Microscopes. Within the last 100, 200 years, we have used microscopes to reveal a hidden world that has been there under our noses the whole time, that we had never seen until we created the technology that allowed us to look into it. These are tiny silica flakes on the eyelid of a beetle. Nobody had ever seen this until we invented the scanning electron microscope. This is crystals of salt growing in a tiny little dish of soy sauce. This is the spiral fronds inside one strand from the stem of a banana leaf. So we have been able to photograph this microscopic world that has been hidden right in front of our faces the whole time. And we have sent cameras and satellites and people into space, and we've taken photographs like this, Earthrise. We've taken photographs like the pale blue dot, our little fragile Earth, hanging there, seen from the other side of the rings of Saturn. We photographed the pillars of creation in the Eagle Nebula, 6,000 light years away from Earth. This is a factory where stars are born. And within my lifetime, we have allowed technology and we have used technology to start exploring another hidden world of mathematics and information. Throughout the 1970s, Martin Gardner published a monthly column in Scientific American magazine about mathematics and mathematical curiosities and puzzles. And in October 1971, he published this. This was the world's introduction to something called Conway's Game of Life. Now, as games go, Conway's Game of Life does not look terribly exciting. The rules of the game are as follows. It is a game for 0 players played on an infinite grid that nobody ever wins. Each cell on this grid can be living or dead, or awake or asleep, if you're, squeamish about the whole life and death thing. And the rules are that if a cell has 0 or 1 neighbors, it will die of loneliness. If a cell has 2 or 3 living neighbors, it survives to another generation. A cell that has 4 or more living neighbors, that cell is going to die of overcrowding. And then a cell that has exactly 3 living neighbors, that cell is going to come back to life in the next generation of the game. Now that's it. That is the entire rules of John Conway's Game of Life. And when this set of rules was first published, people used to do this on graph paper. And so they would have to kind of figure out from one generation to the next by calculating it and working things out by hand. But trying to understand Conway's Game of Life using pencils and paper is like going to a museum and seeing those glass cases where they have the butterflies pinned on the wall. And yeah, you can see what they look like, but you don't know what they are. You don't know how they move, how they behave, how they evolve from looking at that. It wasn't until we fed Conway's Game of Life into computers that we really got a good look at what it is that had been discovered here. These are the 5, these will look familiar to anyone who's played Tetris. These are the 5 Tetromino shapes. And if you feed these into the Game of Life and you press play, what will happen is most of them will stabilize within 1 or 2 generations, but then this one over here goes through a couple of iterations and turns into this infinitely repeating pattern. And as soon as people started using computers to explore the Game of Life, they started asking all sorts of questions. Are there shapes that will move? Shapes that will actually just make their way across the grid? They discovered this. It's a configuration called the glider. They said, are there configurations that will grow infinitely? It was Bill Gosper, a computer scientist in the US in the 70s. He and his team discovered this thing. This is Gosper's glider gun. They discovered another pattern here, which was a thing called the eater, which would allow you could crash these little gliders into it. And when you crash the glider into it, it disappears. And that meant that we now had a way of creating a signal and a way of destroying a signal. We had 1 and 0, true and false. And so the next question is, well, if we got true and false, can we do logic in the Game of Life? It turns out the answer is yes. Let's take a look at this configuration here. We've got 2 inputs, A, B, and we have an output here, which is the logical AND of A and B. Now, if we set our input A to be true, we get no output. If we set our input B to be true, we get no output. But if we set both A and B, oops, let's run that one again. Give me a second here. There we go. So if we set our input A on this thing to be true, then what we are going to get on this is we get no output. This is a logical AND gate, so that conjunction, there we go. Set A is now true, it's lit up in green, but we get no output signal on there. Let's set B to be true here, take a look at what we get, and as the system stabilizes, there we go, we get no output on that. But if we set both A and B to be true on this configuration, take a look at what happens. Get A and B, we push go, we run our configuration, and we have output, logical A and B. And if we can build logic gates in the Game of Life, we can build circuits. And if we can build circuits, we can build computers. And if we can build computers, we can run programs. And there is this program you might have heard about a little while ago. It's a thing called Conway's Game of Life. It's a simulation based on these couple of simple rules. And it turns out that because the Game of Life is Turing complete, you can run life inside life. Now, the Game of Life is just one of a whole bunch of mathematical explorations that are about studying, not trying to solve equations necessarily, not about producing solutions, but about analyzing the behavior of systems as they iterate over time. A lot of the work that has been done in this field falls under this umbrella of what we call chaos theory. You've probably heard of this idea of the butterfly effect. A butterfly flaps its wings in Tokyo today, and then next week in Sao Paulo they have sunshine instead of rain. And weather forecasting was just one of a whole family of systems that was studied by the scientists who eventually got, like I said, classified as people studying chaos theory. And one of the systems that they looked at was to do with complex numbers. Now, still a little high school arithmetic here. We got a piece of grid paper here, and we got this square here, 2 by 2. What's the area of that? 4, yeah. Okay, so now we're going to draw another one. This is -2 by -2. What's the area of that? 4. So 2 times 2 is 4. And -2 times -2 is also 4. And so very quickly, we're like, well, is there a number that we can multiply to get like a square with a negative area? Now, in reality, squares with a negative area don't exist. You want area, you have to actually, it has to be positive. You are occupying some space. But the lovely thing about mathematics is that reality is kind of optional. It can go, well, all right, well, okay, clearly this thing doesn't exist. It's totally imaginary, so there it is. It's called I. It's the imaginary number that I is the square root of -1. If you multiply I by I, you get -1. You all happy with that? And maths goes, yeah, we can work with that. Right, let's go and do some equations, because you can do equations. If you take a number in what is called the complex plane, it is a number that has now imaginary numbers or complex numbers here. Best way to think of these is it's like a project plan. Part of it is real, and part of it is imaginary, and it is no use at all in predicting what it is that is going to happen next. So if we take one of these numbers with an imaginary part and a real part, pardon me, we can do arithmetic with it, just like you did in high school. We're like, we want to multiply this together, and all you got to remember is anytime you get I times I, it flips from being positive to negative. So you can expand out the brackets, and you can crunch these expressions down, and you see there we got 1.2i times 1.2i, so that becomes minus 1.44, and then you just collapse the red bits and the blue bits, and there it is. We can do maths with these things. Now, in 1918, a French mathematician, Gaston Julia, published this paper, the Memoir on the Iteration of Rational Functions. And as I said, this wasn't about finding solutions. What Julia and his colleague Pierre Fatou were doing was they were looking at how do functions behave when you run them over and over and over again. If we take x goes to x plus 1, and it's okay, 0 goes to 1, 1 goes to 2, and you can see immediately, like, you instinctively know that this is just going to keep getting bigger. If we say x goes to 2 minus x, well, 0 goes to 2 minus 0, 2 goes to 2 minus 2, which is 0, 0 goes to 2 minus 0, and again, within a couple of iterations, you're like, yeah, I can see how this thing is going to unfold. If we take, say, x goes to x squared, 2 goes to 4, 4 goes to 16, 16 goes to 256, and off we go, galloping towards infinity. If we start with a number below 0, we go 0.5 to 0.25 to 0.125 to point something very small, and we converge towards 0. We get smaller and smaller, although we never actually reach it. But now what we're going to do, we're going to take one of these numbers in the complex plane, and we are going to take that number, and we are going to say every time around, it's going to go z goes to z squared. So we're going to take 0.7 plus 0.8i, we're going to square it, and it's going to move over here. And then we're going to square it again, and it's going to go over here, and we square it again, and it ends up over here, and we square it again, and there it is, and then, boom, it goes galloping off towards. Now, there are 4 different infinities on this graph. I realize it's early, but there are 4 infinities. There's a positive and a negative real one, and then there's a positive and a negative imaginary one. So you're cool with the idea that there is an imaginary negative infinity? Cool, let's move on. So we're going to take another point on this graph, this one here. 0.9 plus 0.8i. That goes straight off down there. Now 0.8 plus 0.8i, woo, real positive infinity. 0.7 plus 0.8i, that goes off to positive imaginary infinity. But this one, this kind of hangs around for a while. And you watch what it's doing, it's like, oh, is that gone into a circle? No, it thought about it, but it didn't. Oh, there it's going the other way. No, no, hang on. Is this stable? Is this going to stick around with us? And eventually it goes, you know what, I'm bored, and it is just going to go galloping off towards negative imaginary infinity. After something like 36 generations. This blue one here, boom, straight down the hole in the middle. 0.4 plus 0.8i, ding, 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 and straight down the hole in the middle. Now, these initial points, these are right next to each other on that graph. And the question that arises from this, the first person to study this question was this guy, Benoit Mandelbrot. Mandelbrot, his family were Polish. He was born in Poland. He spent his childhood in France. He went over to the United States, and he had an awesome job. He taught mathematics at Harvard, and when he got bored of teaching, he'd go over to IBM, who had one of the computers in the world at that time, and they'd let him play with it. And then he'd go back to Harvard and he'd be like, hey, check out this cool thing that I got the computer to do, which sounds like a lot of fun. And he was fascinated by the mathematics of nature. He had this very famous quote: clouds are not spheres, mountains are not cones, coastlines are not circles, bark is not smooth, nor does lightning travel in a straight line. And the reason why his name has gone down in history was thanks to this. Z goes to z squared plus c. You take a point on that complex grid, and you square it, and you add the number you started with, and you square it, and you add the number you started with. And what he and his team did is they said, right, we are just going to plot a very simple graph, and if that point on the grid disappears off towards infinity, then we are going to leave it blank. Otherwise, we are going to print a star, because that's all they had. They didn't have color displays. They didn't have high definition. They didn't even have screens. They had teleprinters. And so they crunched this algorithm, and they became the first people in history to see this, the Mandelbrot set. Now, the algorithm that some of you here have probably implemented, it's kind of like a rite of passage for a certain kind of a maths and programming geek, is what you do is you take a square and you see how quickly does it go infinite. And if it goes there immediately, you paint it blue. And if it takes a little while, it's purple. And if it takes a really long time, like 100 generations, you paint it red. And if that never converges to infinity, if it disappears down to 0, then you color that in black. That is the algorithm that we use to plot this. Now, what we are going to do now, the amazing thing about this shape, this structure, is that from that z goes to z squared plus c, there is a literal infinity of detail in this. We're going to start at, how big is that screen there? That's about, what, 5 meters across, maybe 6 meters? So we're going to start zooming in here. And this shape is going to get bigger. And so around about now, let's say that's magnification factor 1. So 2, 3, 4, 5. Here, 10. The original shape is now bigger than this complex that we're in. And we're going to keep zooming in and keep zooming in. And around about this point here, the original shape is larger than Stockholm. And we're going to keep zooming in. And you notice we're not getting down to pixels or anything. There's more and more detail. The original shape is now larger than Europe. And we can keep zooming in. And 10 times Europe, well, at that point, you're kind of talking about the size of the planet Earth. And we're going to keep zooming in, and we're going to keep magnifying, keep magnifying. By the time we get to around about here, the original shape there is probably bigger than our solar system. And we can keep going in forever. And at points buried in the structure of this thing, you find these. They're not copies. This is not a repeating pattern. This is self-similarity. It has echoes of its own structure at an infinite level of details. Now, some people have called the Mandelbrot set the thumbprint of God. I'm not a terribly spiritual person, but I like to play games. And one of my favorite experiences in a computer game is when you go off on some weird side quest. Like there's a piece of scenery, you're thinking, can I stand on that? And you spend a couple of hours trying to figure out, and eventually you get there, and you find something that the creators of the game buried there, just to say, yeah, you're on the right track with this. And so, this thing, the Mandelbrot set, to see this picture, we had to invent imaginary numbers. We had to invent complex arithmetic. We had to invent computers that were fast enough to crunch these numbers in, hundreds of millions of billions of calculations per second. And remember, a computer is just what happens when you stick lightning inside a rock until it figures out how to think. We invented all of this stuff, we plugged it all together, and we got this. And I think that's kind of cool. I think there's a certain beauty in that. Now, this was groundbreaking when we first began to see these kinds of images, because no one had ever seen them before. And, just putting a picture on the screen of a computer, that used to be a pretty big deal. But then, first science and academia, and then industry, and eventually Hollywood was like, we could use computers to do stuff. And 1982, we had Steven Lisberger's Tron, which was it was disqualified from the Oscars because using a computer to make the graphics for a film was cheating. And it was, They did eventually apologize and go, okay, our bad, and they gave Tron a Lifetime Achievement Award. We had Luxo Jr., Pixar's first full-length animated picture. We had Jurassic Park with the computer-generated dinosaurs on the screen with real people. We had this guy. Now, who is this? Is this Peter Cushing, who is a dead British actor who has appeared in Star Wars? Or is this Grand Moff Tarkin, who is a fictional character owned by Lucasfilm Limited, who is now owned by Disney? You know, the lawyers are still trying to figure out exactly what's going on. But we now have a point where I saw a review of this movie which said, you know, computers now, we can have dead actors playing living characters and living actors playing dead characters. Hollywood can do anything. We can put anything you can imagine on a screen. We can answer really important questions, like what would happen if they remade Friends, but they got Nicolas Cage to play all of the parts?
Boy, that was terrific.
Really bitchin'.
Now, the technology that we use to solve important questions like that one is something called a convolutional neural network, and it's based on pattern recognition. If you ever, you lie on your back in a field on a sunny day and you see clouds kind of drifting overhead, and your brain tries to turn those clouds into shapes that you recognize. Like there's a rabbit, and that one looks kind of like a face, and and we have figured out, well, I don't say we figured out a way of teaching computers to do this. But it's more accurate to say we figured out a way in which computers can figure this out for themselves. What we do is we take a stack of labeled inputs. We say these pictures are cats, these pictures are dogs, and we feed it through layer after layer after layer of these self-reinforcing pattern recognition routines. And eventually we get a system that we don't entirely understand it, but we know now that that system can probably tell the difference between, say, a dog and a muffin. Now that might not sound like it's a terribly difficult problem. You know, a dog's a dog, a muffin's a muffin, but actually it can be more complicated than you think. Now, this is serious business, your muffin and dog discriminator, that's a very, very important algorithm. But this is where people like me are like, what if we wire it in backwards? What if we take the dog detector, and instead of using it, we put in a picture of a dog and get out yes or no? What if we take a picture, put the dog detector in reverse so it becomes a dog amplifier, and then we feed in yes, and the computer goes, please don't do this. And we say, no, come on, I want to see what will happen. Now, I know, here in Stockholm, people love dogs, and there's dogs all over, so I came into the venue last night, and I got a picture of it while it was empty, and I was like, come on, we're going to find the dogs. And the computer says, there's no dogs in this picture. And I say, but what if there were? Enhance them. And it goes, I'm not sure about this. And I'm like, no, come on, increase the dog amplification. And it says, please stop. And I'm like, no, come on, let's go one more step. Let's see what we can do. And we start getting images like this one, these bizarre kind of psychedelic dreamscape images. And the reason why images like this are kind of so disturbing is that it's based on the same kind of system that our brains use to recognize dogs. But obviously, there's no dogs in the picture. If you glance at it out of the corner of your eye, you're like, that's an eye, maybe that's a foot, that's a nose, but then you look closer and it's not. And this is because convolutional neural networks are based on that same kind of idea of pattern recognition, but you turn them backwards, you get a dog amplifier, and you get a completely new kind of art. It's called deep dreaming. The Deep Dream was the Google project that first kind of pioneered this. Now, we've looked at a whole bunch of ways that you can use computers to create art, computers to make movies, computers to draw pictures. But what about if the code was art? There is this ongoing discussion about what programming is. Is programming a science? What are we? Are we scientists? Are we engineers? Are we developers, creators, back-end, front-end hackers? Is code art? Is it science? Are we just glorified typists? And I've reviewed some code in my time, and I've looked back on code that maybe I wrote a little while earlier in my career, and I've looked at it and I've gone, this isn't science. And it's not engineering, and I wouldn't call it art because I don't think they were trying to say anything here. But there is good news, friends, because there is a safe space for these kinds of programs now. The International Obfuscated C code contest. The goals of the contest are to write the most obscure or obfuscated C program, to show the importance of programming style in an ironic way. That means we do it badly as a warning to others. to stress C compilers with unusual code, and to illustrate some of the subtleties of the C language. And finally, to provide a safe forum for poor C code, so we can share this and appreciate it. Here is a recent submission. This is program.c, and what this does when you run it. Now, the best thing is you look at the code, you're like, any C developers in the room? Any of you want to read that? Tell me what it does. What does it do? Should we just run it and find out? Because that's the best thing to do with code that looks weird. We're just going to run it. And what do we get? This is Flappy Bird, running in a 80 by 32 Linux terminal. Now, and it's every bit as difficult as Flappy Bird is on real systems as well. Now, this one here, this is another submission from a couple of years ago. Again, this is in C. Let me zoom out to make it a little bit easier to review the code here and see what it does. And it turns out this is it's a Mandelbrot Set Generator in C. I like that. I mean, talk about self-documenting code, you know. Now, this thing here, this is 1,022 bytes of JavaScript. And if you copy this and paste this into a web browser, it plays chess. And I don't mean it draws a chessboard. I mean, this is a chess engine. This thing can beat me at chess in less than a kilobyte of JavaScript. It's written by a guy called Oscar Toledo G, and there are some wonderfully elegant hacks in here. But this, you know, is an astonishing example of being able to do something really sophisticated with an incredibly small amount of code. Now, in 1994, a guy called Simon Rysinkevich submitted this to the International Obfuscated C code contest. This is an empty file. It has 0 bytes. And at the time, there was a popular C++ compiler that if you gave it an empty file, it would compile a valid executable that produced no output. And so the accompanying note said, this is a quine. This is a program that prints its own source code. And the judges went, OK, we're going to give you this on a technicality, and then we're going to change the rules. So after that, all obfuscated C code had to be at least 1 byte in length. Otherwise, they're like, well, that's just the same as Simon's submission from '94. You can't do that again. But this brings us onto the idea of quines. Anyone read this book? There's a bit in here where he talks about William Ormond von Quine, who was a philosopher who studied self-referential statements. And a quine is a program that prints its own source. Now, it can't just read it off disk and print it. It needs to be a program that creates a data structure that when you output it, gives you back the code to your original program. Now, I haven't done Java in a little while, but I figured, you know, since most of you here are Java devs, I was going to dust off my old rusty Java chops. Last time I was writing Java for money, web TVs were still a thing. That gives you some idea how long it's been. There's probably people in here who've never seen a web TV. But so I figured, OK, let's figure it out. Let's write a quine in Java. So we got a public class quine. We got a void main. And what I want to do is I'm going to use the triple quoted string literal here. So the first thing I need to print is I need to print the public class. OK, and then I'm like, ugh. And very quickly, I'm like, this isn't going to work. Because every time I do this, I'm just making another layer of abstraction that I then need to factor into it. So let's backtrack a little bit. Maybe what we could do is we could use self-referential string formatting. To write quines, you have to find loopholes in the design of the language, the places where the language designers divided by 0 and they left a little gap that you can kind of sneak through. So I'm like, OK, well, what if we put this in as a format string? And then we feed that string back into itself along with a quoted string literal. And if you do this in Java, you get your own source code back out again. This is a Java quine. Now, in JavaScript, all functions have a 2-string representation built in. So any function, you just say, run this, function.toString, and it works. And in ECMAScript version 6 and higher, this is a quine. And I saw that, and I was like, no, it's not. That's ridiculous. Look at it. So I copied and pasted it, and I ran that in the console on a web browser. And sure enough, when you run that expression, it outputs itself, which says everything you need to know about JavaScript. And whether you think that's good or bad, that's entirely on you. So with procedural languages and object-oriented languages, yeah, we can make things that print their own source code. What about declarative languages? Could we make a web page that is its own source? Now, there's a guy called Leon Bambrick who came up with a brutalist HTML quine, which I thought was brilliant. And I took that idea and ran with it a little bit. So this is a web page that prints its own source code. And here is the source behind this. Now, the first thing we're going to do is we're going to put a rule in here that says we're going to add some CSS. Everything on this page displays as a monospaced block. Now, this is a terrible idea. But do it anyway because you might learn something interesting. When we reload our page, we can now see the source code to our CSS. So let's go back over here, and we're going to say, all right, if you see an HTML tag, put one of these before and one of these after it, and we run it again, and there's HTML at the top. /HTML, that's off the bottom of the screen. I mean, where would you put it? We've just said, when you finish rendering the entire web page, draw this after the end. You know, what's the browser going to do? So now let's jump back over here. We'll plug in a couple more of those, a style and a /style. We'll put some white space formatting in. Now, there is no kind of automated way of doing this, so we just got to put in head, body, title, anchor, paragraph. There we go. But we've got before and after on all of those. And now we have this. We have a page where we can see all of the tags. We've got a link on this page, and that link has an href. We want that href to appear in it. So we can go back over here, and we can use a CSS selector that says, if you see an href, inject this content before it and include that attribute in the injected content. We go around again, there we go. Now we can see where our link is actually going to. Last thing we're going to do is just put a margin on there and drop the height of that down to 1 pixel, and there it is. This web page now prints its own source code. Now, you'd never do that, and I hope you'd never do that in production. Hands up if you, no. I learned things about HTML that in 20 years of web development I'd never seen before, just by pushing the limits of the language and the compilers and the interpreters, seeing what I could get them to do. Now let's take a look at a little piece of code here. What language do you think this is written in? Hands up for C. It looks kind of like C, doesn't it? We got a hash include and a standard io.h up there. And if we put some syntax highlighting on it and take out the comments, there we go. I mean, it's not brilliant C, but it's clearly some C code. But hands up if you think it's Ruby. Because if we put Ruby syntax highlighting on it, and we highlight the string literals, there we go. That's perfectly valid Ruby code. Again, it's not pretty. So which one is it? Well, I guess there's really only one way to find out. Let's run it. So I'm going to take that program there. And just to prove I have nothing up my sleeve, there is polyquine.c. And then I am going to run this through the GCC compiler. And I am going to get an output file. There's a warning, but come for the warnings, kids. This is not that kind of a talk. Now we're going to run it, a.at, and there we go. We've got our original program back again. So now what happens if we run it through the Ruby interpreter? Well, let's Ruby polyquine.c, and ooh, look at that. We've got our original program back yet. While we're in here, let's run it through Python and see what happens. And there it is, and oh, that's nice. And just while we're in here, what about Perl? Any Perl developers in for JFocus this year? Look at that. Now this program prints its own source code in C, in Ruby, in Perl, in Python, and if you can find a compiler that doesn't complain about main returning void, in C++ as well. This is a thing called a polyquine. It's a program that's valid in multiple languages. Now then, take a moment to digest this wonderful little snippet of code here, and I want you to figure out what language this is written in. Because we got a system.console here, which that looks to me a little bit like .NET, because we got console with a capital C. And we got an XML, XSL namespace here, so maybe that's an XSL transform. And we got a for each, we got a console.log lowercase, that smells a little bit like JavaScript, and we've got an Ada text-to-IO procedure up here. Any Ada devs at JFocus this year? Probably not, but if you are, you might recognize this, and we've got a begin in block capitals, which is a serious business language from the 1970s, which will be either SQL or COBOL. And then we've got Act One, Scene One, Enter Ajax, which doesn't even look like programming at all. You know, that looks like plays. Now this is a thing called the Ouroboros quine. It's created by Yosuke Endo, who's one of the core contributors to the Ruby language. It is a Rust program that produces a Ruby program, that produces a Rex program, that produces a Scala program that takes you right around a circle of 128 languages, and at the end, you get your original source code back out again. And that's not the cool part. The unobfuscated source code to this thing, or rather the zoomed out source code, I think unobfuscated is probably the wrong word, it looks like that. That's not the cool part. If we zoom in on the other corner of this piece of source code here, it's future-proof. It's got scope in it to repair bugs and things in the program. There's this buffer in there. That's not the cool part. The cool part is that every single one of those 128 languages is available on Aptitude. You can apt-get install it on Ubuntu Linux, which means that there is a GitHub Actions continuous integration runner for this thing that installs all 128 languages, runs around, and if it gets the original program back at the other end, then the tests are passed and the build is green. That, I think, is pretty cool. But let's backtrack a little bit. Act 1, Scene 1, Enter Ajax. What is going on there? Well, that is an esoteric language. It's a language called Shakespeare, which is designed to allow you to program the computer with things that look like Shakespeare plays. The way that Shakespeare works is your acts are namespaces, your scenes define block scope, you declare your variables by having them come onto the stage, and then they talk to each other. And if you say something complementary, if you flatter another variable, that variable becomes incremented. If you insult a variable, it is decremented. So here we go. We have Romeo and we have Hamlet. Act 1, Scene 1, enter Hamlet and Romeo. And Hamlet says to Romeo, "You lying, stupid, fatherless, big, smelly, half-witted coward. You are as stupid as the difference between a handsome, rich, brave hero and thyself. Speak your mind." Now what that does is it increments Romeo until it contains the ASCII code for the letter H, and then it prints it. Now, to do Hello World, to do E, "You are as brave as the sum of your fat, little, stuffed, misused, dusty old rotten codpiece, and a beautiful, fair, warm, peaceful, sunny summer's day. You are as healthy as the difference between the sum of the sweetest, reddest rose and my father and yourself. Speak your mind." E. Hello World in Shakespeare is about 3 pages, but you know, the Bard was not noted for brevity. Hamlet is one of the longest works of notable literature in the English language. Let's take a look at another example. Anyone recognize this language here? This is whitespace. This is a program written in whitespace. Let me help you out. Those of you who might not have seen whitespace before, this is whitespace with syntax highlighting applied to it. And in whitespace, the only things that matter are tabs and spaces. It ignores everything else. Which means if you want to, you can hide whitespace programs inside C programs, and you've got a program that does something different in 2 different languages. Now, there are a whole bunch of these esoteric languages, but the ones that I particularly enjoy are the ones that aren't trying to hide a programming language inside another programming language. They are hiding computer programs in something that looks like it has nothing to do with computers. There is a language called Chef, where all of your programs look like recipes. And the idiomatic Hello World souffle in Chef is this. 72 grams of beans, 101 eggs, 108 grams of lard, 111 cups of oil, 140. Anyone hungry? Like you're looking at this and thinking, yeah, I could go for 33 potatoes right about now. So, you know, it's a plausible recipe, but it's not, you know, something you'd actually want to sit down and eat. But a guy called Mike Worth, he sat down with a copy of the Chef spec, and he came up with this, the Hello World chocolate cake. And this is a real cake. He actually baked this, and he served it to a bunch of friends. And this is it's a Hello World program, but it's also a recipe for a chocolate cake with a chocolate sauce built into it, which I think is brilliant. You run it on a computer, Hello World. You run it in your kitchen, fika time. Now, let's have a look at how to square a number in Pete. This program, and this is a program, this is the source code for squaring a number in the programming language called Pete. It is a graphical language named after Pete Mondrian, the Impressionist painter. The instruction set that exists in Pete is dictated by what happens when you cross from one color into another. So this is our standard color palette. The instruction set is at the top there. So we're going to run through this now in the debugger. We're going to see what we actually get. So your instruction pointer starts in the top left corner, traveling east. So we cross from light blue into dark green. That prompts you for input, asks the user to input a number. When we hit a black boundary, the pointer is going to change direction. We cross from dark green into dark red. That says take the value on the top of the stack and duplicate it. So now we have 2 copies of that. We're going to cross from red into yellow. That says multiply. Pop 2 numbers off the stack, multiply them, and put the result back onto the top of the stack. Then we cross from yellow into red. That is output. Whatever's on the top of the stack, pop that out and put it up on the screen. Then we are going to cross the white area here. That's a no-op, no operation. We get to the edge of the grid. We are going to turn right. We are going to keep following this blue area until we end up with black on all sides, and that means halt. That means you've come to the end of the program. Now, this is Hello World in Pete. Now, I want you to imagine you hung that up on the wall in your house. How many people do you think would realize that the thing hanging on the wall was a Hello World computer program? Again, I think it's a fantastic example of hiding code inside pieces of art from a completely different discipline. Now, you're going to see over the course of the next couple of days, you're going to see some talks. You're going to see some interesting technology. You are probably going to see some live demos. Because, live demos are very much part of the appeal of going to conferences. And live demos are exciting. And they're exciting because they might not work. Because there is always this element of risk when someone's going, right, we're going to do a live demo, and you're thinking, okay, this is probably going to work, but what if the Wi-Fi goes down? What if this thing doesn't work? What if they make a mistake? What if there's some kind of problem? And that's what makes this thing exciting. And as an industry, we don't like exciting. Conference is fine, but you don't want deploying your code to production to be exciting, because exciting means it might not work. And so we have gone to great lengths to eliminate all of the variables, other than obviously the ones in the program that make it work. We have automated environments, we have infrastructure as code, we have unit tests, integration tests, red, green, switching between environments, all this kind of stuff, all of which is designed to make things reproducible. To mean if we do the same thing twice, we can guarantee we are going to get the same result come out of it twice. And we even have this term that we use for systems which have not been subjected to this kind of engineering rigor. We call them snowflakes, snowflake servers. Like, don't touch that machine. Why not? That's the machine that runs the payroll. No, don't touch it. Don't update it. Don't patch the security vulnerabilities. If you patch it, the payroll will stop working and nobody will get paid. We're working on it, but in the meantime, that server is special. Don't even shut it down. If we shut it down, it might not come back up again. And these are snowflakes. They are special and unique. But if you pick a snowflake, an actual snowflake out of a blizzard, and you just sit and you watch it melt on your hand, you've just been part of a unique experience, Nobody else, every snowflake is unique. That's why we use this word. But nobody else will ever have seen that exact snowflake that you just sat and you watched melt. That was part of an experience, and being part of an experience like that, an experience that can't be automated, can't be recorded, that's what makes live demos and live performance exciting. And that's what gets us onto the idea of code as a form of performance art. Now, the guy over here under the big screen, this is Sam Aaron. And he's in the Royal Albert Hall here with the London Philharmonic Orchestra. And Sam is the creator of a thing called Sonic Pi. Sonic Pi is a musical programming language. Sonic Pi is designed to write programs whose output is not images, it's not text on a screen, it's not web pages, it is music. Now, we're going to do a little live demo of Sonic Pi here. First of all, we are going to play the note A3. Now, one of the interesting things about Sonic Pi is that it runs all its instructions in parallel unless you tell it not to. Imagine if Java did that. So if we want to do things one after another, we got to break it down and put delays in between them. So we've played a couple of notes there, but where it gets interesting is it has its own proper programming language. It has loops, it has conditionals, and we can, now that's not very exciting. So what we're going to do is we're going to crank up the tempo, 244 beats per minute, and then we're going to change that little sine wave noise. We're going to use something called, I think Texors is the synth noise that I'm going to use in this, which is kind of nice. So we're going to get this, there we go. We get this bass line going. Now where this is going to get interesting, let's take that, and what we're going to do is we're going to wrap that up in a loop. And we're going to call this is a thing called a live loop. Now, a live loop means you can run other loops that are synchronized with it. So all these loops will always start at the same point. And now I'm going to put another live loop in. I'm going to sync this against the main loop. And I'm going to play this sample here, the closed drum cymbal, 15 times. And then I'm going to play the open drum cymbal. You hear that? And those two things are going to stay in sync. We haven't had to restart the program. We haven't had to stop, restart anything. I'm going to paste in this block of code from another buffer. This is going to give me a kick drum and a snare drum. And now I'm going to come over into my main loop method here. here, and I'm going to put a counter variable in there that increments every time we go through that loop. And then I'm going to say, well, if the factor, if I is divisible by 3, I want you to play this note instead. And then I'm going to say, well, if I is divisible by 5, I want you to play this note instead. Some of you might be recognizing the algorithm we're implementing here. And then finally, you can guess what's coming next. If it divides by both 3 and 5, so by 15, I want you to play this note instead. We've implemented FizzBuzz in music. You know, classic screening interview exercise for people applying for jobs everywhere. Write FizzBuzz, and this is the FizzBuzz riff. And remember that, because that's going to come up again in a moment. Now, Sonic Pi is absolutely fantastic. It runs on Raspberry Pis, and it was designed as a really kind of accessible way of getting kids interested in programming who maybe aren't old enough yet to care about things like web pages, but music is a universally human experience. It's something that all of us can relate to. Now, I have talked so far about a lot of cool things that other people did. I want to wrap up today by talking about something that I did. Now, some of you may have, at certain points in your career, been looking for a new gig, and you've gone online and you've searched for developers, and you've seen companies trying to hire a Rockstar developer. And there we go. We got a Rockstar senior front-end developer to join our team, Rockstar JavaScript and Node.js. We got a Rockstar senior Java software developer. And this is a thing that's kind of bubbled around in our industry for, well, certainly as long as I've been working here. And then a few years ago, Paul Stovall posted this on Twitter. He just said, to really confuse recruiters, somebody should make a programming language called Rockstar. And I had this experience. I had this moment of a blinding divine revelation. This is my purpose. This is what I was put here to do. Because I wasted about half of my youth trying to get the Amstrad 128 to play BMX robot games and stuff. But I wasted the other half on fine individuals like these people here. You know, the great rock and metal bands of the 1980s with the really tight trousers and the big hair and the pointy guitars. Shout out to Joey Tempest and Europe up there. And I thought this is what the world needs. The world needs a programming language where all of your programs are also heavy metal songs. And so I invented Rockstar. Now, I invented Rockstar in a bar as a joke. I was sat in a bar waiting for some friends. They were late. I saw this tweet, and I thought, I wonder if you could actually come up with a language spec which would let you compile heavy metal lyrics. And I started kind of playing around with some ideas, and I thought, okay, well, hello world in Rockstar, how do you do output? Well, let's just have, say hello world. It's dynamically typed. We're not going to worry too much about things like semicolons, that kind of stuff. But maybe we need more than one way of doing something. So you can be emotional and poetic in your program. So you can scream hello world, or you can whisper it, or you can shout it. I thought variables and assignment, how are we going to do that? Now, some languages, you need to declare the type, variable, equals sign, value, semicolon, var my underscore string equals hello world, the message equals jfocus rocks. And I looked at this and thought, okay, one, dynamic typing. Yep, we can get rid of the types, and also we can get rid of the semicolons. We'll just kind of figure that out later. It's easy to invent programming languages in a bar because you can do anything you like because, hey, it's never going to matter, is it? And then I thought, well, that equals thing there, equals isn't very rock and roll. Can you think of a song where it's got the word equals in it? It's like is, X is 5. My string is hello world. All right, so we'll swap that out. And then I was looking at, my underscore string and the message with this weird Pascal casing thing in it. And I saw a talk that Douglas Crockford gave a couple of years ago. And at one point he says, we have these arguments in our industry about Pascal case, camel case, kebab case, snake case, chainsaw case, all these different ways of capitalizing things. And he said, what we want the whole time, we want variable names with spaces in them. These arguments are just because we got a variable that includes 2 words. And I thought, all right, we can do that, easy. Now, I didn't go completely free-for-all. What I decided is that there's 3 different kinds of variables in Rockstar. There are simple variables, which work like they do in Ruby and Python. There are common variables, which have to start with a prefix. My, your, the, and a. So you can have variables, my heart, your dream, the night. And then a proper variable's got to have capital letters, so you can write programs that are songs about people, like Dr. Feelgood and Black Betty and Billie Jean. Now, In programming, we initialize variables a lot with values that are often numeric, and numbers are not very rock and roll. After 1, 2, 1, 2, 3, 4, it all kind of goes downhill from there. So I wanted a way of initializing numeric variables without having to use numbers. And so what I came up with was, well, what if we take the lengths of the words, modulo 10, and treat those as decimal digits? So now we can initialize 3, 5, and 100. Fizz is ice, buzz is dying, the limit is a love-struck lady killer. This is good. We're on our way to being able to do fizz buzz, which means we can interview people for Rockstar developer roles. What about floating point numbers? Well, you know, in C#, decimal pi 3.141596, and in JavaScript, var pi equals 3.141. And honestly, if you're going further than that in JavaScript, you're not getting that precision back, you know. Don't worry too much about the details. But in Rockstar, to initialize a floating point variable to the value of pi, my heart was ice, a life unfulfilled, waking everybody up, taking booze and pills, 3.14159265535. What's not to like? Arithmetic. Now, you listen to people talk about maths, they don't say things like plus and minus. They say, oh yeah, the total is the price with the tax. It's the subtotal, that's the total without the tax. Multiply, we need the quantity of the product, and you know, your speed is your distance over time. This is fine. But because we've used these poetic-sounding arithmetic operators, we can write operations like a girl with a dream, a man without a face, the wings of the night, a whisper over the water, yeah? We need comparison operators. Your love is a lie, true or false? The whiskey ain't the answer, true or false? My heart is stronger than steel. My soul is weaker than water. My will is as strong as a lion. Your lies are as low as a snake. Now, you can't program without functions, not really. So you think about how you describe a function. Say we want to do an arithmetic modulus using the technique of repeated subtraction. So you're like, okay, well, the modulus function, it takes a number and a divisor, and then while the number is as high as the divisor, what you need to do is subtract it. So you put the number without the divisor, put that into the number, and then give back a number. The blank line in there, that's how we delimit blocks in Rockstar, like the way you delimit verses and choruses in rock music. Or midnight takes your heart and your soul, and while your heart is as high as your soul, you put your heart without your soul into your heart, and you give back your heart. Now, I'm 3 beers in, my friends have arrived. I'm like, yeah, that'll do. I stick this up on GitHub, parody specification, that's it. And I stick it up on Twitter, and I'm like, hey, look, I wrote a spec for a language, a proposal for a Turing-complete programming language in which you can write programs that are also 1980s power ballads. And I put it up on the internet. I went to bed, and the internet found it. And the internet liked it, and Hacker News got hold of it, and people started saying nice things about it. It made a Boing Boing magazine. Cory Doctorow did a thing about it. People on Reddit were leaving comments like, how come goes to 11 isn't a reserved sequence of keywords? This person, I would love to be a certified Rockstar developer. Thank you for that idea. We'll be seeing more about that in a second. The docs are hilarious. I'm sold. Shut up and take my money. I got an email from Classic Rock magazine, which is not anything to do with computers or technology. It's a serious music magazine that interviews like Metallica and the Rolling Stones. And they're like, what is this Rockstar thing everyone's talking about? I'm like, what do you mean everyone's talking about? So I got in Classic Rock magazine for inventing a joke programming language. Now, I don't know if 16-year-old Dylan would think that was the coolest thing ever or the lamest thing ever, but I don't care. I still did it. But then something happened that I really did not expect. People started filing issues on the GitHub repo. And I was like, why are you filing, you know, why do you care? And they said, my implementation has undefined behavior. And I was like, I'm sorry, you're what? People had implemented this. Somebody had taken the spec that I wrote in a bar, and they had implemented it in Scala. It took them about 3 days, and then they were like, here, the spec is ambiguous. I don't know what the behavior should do. Somebody else did a Python transpiler for it. Somebody built a Rust interpreter for Rockstar. And I was just, you know, blown away by all of these people jumping in on this thing, and it didn't go away. Just kind of, you know, the attention and the stuff about it, you know, the interest in it would kind of wait, and then it would pop up again. Someone else would find it. It would make the front page of Reddit again. And eventually, you know, I decided maybe this needs to be more than just a parody spec with a bunch of implementations. Because, you know, Scala and Rust, those aren't accessible mainstream languages. Most people do not know how to install Scala in order to become a Rockstar programmer. Because let's face it, Rockstar programmers don't use Scala. That's not what any of this is about. I thought, if we really want to make this available to the world, it needs to run in a browser, so you can just open it up on your phone. So I built a Rockstar interpreter in JavaScript. Never build interpreters in JavaScript. When you stare deep into the abyss, it gazes back into you. But I did it, and it's live, and it works. And if you go to codewithrockstar.com right now, there is an online interpreter that any of you in here, you can go on that on your phone right now, and you can try out some Rockstar code. And if it works, you can come up and see me after the talk or later on today, and I will give you your wipe clean, self-adhesive, certified Rockstar developer certificate that you can put on your laptop, so when you walk into that job interview, they know they don't even need to bother asking you any questions. They're just going to hire you. Now, you notice the logo type in the Code with Rockstar website there. I wanted something that was complete, like over-the-top, out-and-out 1980s glam metal excess, and I thought, let's see if I can maybe riff on some band logos. So I looked at, you know, Metallica and Iron Maiden, Def Leppard, all these bands. I didn't find anything that was quite right. And then someone said, have you thought about Microsoft Consumer Products, 1980 to 1982? And they weren't using this logo anymore. So what I did is I took that logo and I upcycled it. So there we go. Thank you very much, Microsoft, for letting me upcycle your logo. As I said, all of you here, if you want to become a Rockstar developer, this is your big chance. Hack out some code on your phone. Come up and see me afterwards. And we're going to close out now. We saw the chocolate cake written in Chef, and we saw the Mondrian Hello World. And so the real test of whether Rockstar succeeded as an esoteric language is, can we write a Rockstar program that if you didn't know what it was, you'd just think it was a bad 1980s heavy metal song? And so I'm going to close out now by performing live for you. Ooh, this is interesting. I'm tangled in a big cable. There we go. That's nice. J-Focus, here's FizzBuzz in Rockstar. Takes your heart and your soul, and while your heart is as high as your soul, put your heart without your soul into your heart. Give back your heart. You remember FizzBuzz? A love-struck lady killer. My world is nothing. Fire is ice, hate is water, till my world is desire. Build my world up. At midnight, taking my world, fire is nothing.
and midnight taking my world. Hate is nothing. Shout fist buzz, take it to the top. In midnight taking my world. Fire is nothing. Say this, take it to the top. In midnight taking my world. Hate is nothing. Say buzz, take it to the top, top. Whisper my word.
Thank you, J-Focus. That is all from me for now. Me and the guitar will be around at the party this evening, ruining some of your favorite songs for you. Have a wonderful time. Enjoy the rest of the conference. What was it you said, Matthias? Educated, enlightened, inspired, and entertained. I hope you hit 10 out of 10 on all 4 of those. Thank you very much.
Whoa, thank you. Great. Thank you very much. So, I guess you will know what the entertainment will be in the bar tonight. So I guess you will be coming back at bar 5. I don't know.
I'm going there now.
Yeah, around like.
I'm just going to sit in the bar and get warmed up, you know.
Perfect. Round 8 or something like that.
About 8 o'clock tonight. So yeah, head up. We'll be in the bar up there.
Yeah.
It'll be fun.
And since we're able to get hold of him, we wanted to get as much of Dylan as possible at J-Focus. So there's also a talk by him tomorrow at 2 o'clock, I think, at C1, so don't miss that.
There is?
Huh?
There is?
There it is. Perfect, right?
I'm glad you told me.
Yeah. And I guess that's it then. Now there is a small break and all the sessions are starting up again at 11 o'clock. Also, install the app. In the app, you can also rate all the talks and send comments and feedback to the speakers. To do that via the app, please. Have a great conference.